So, trying out some more stuff here in Chapter 11, trying to see what we can do with our our new software here as I test these out. This is the chapter on statistical inference using variability and variance in this case. So we're concerning ourselves with sigma squared and s squared. And what we need to do is discuss what is the idea of sigma squared, s squared, and the use, but through chi-square. Building the confidence intervals for the population variance, testing their hypothesis, is it more or less or equal to something, and then moving on to see if we can compare two different variances using something called the F distribution. So you're going to start off with the Z, then the T, now the chi, and then the F. And the F is probably the most important one we'll see now and throughout because it'll tell us whether or not something is significant in our ANOVAs and our regressions as we move forward. We can take that F distribution and do confidence intervals as well as hypothesis testing when we look at two different variances. So to start, think of it this way. We're just drawing this sample. Hopefully it's large. Hopefully it's at least size 30. At least that's what we want it to be. And that sample is going to have some statistics to go with it. There are point estimates. You're going to have X bar and you're going to have S. In that case, sample standard deviation. You can also have the variance, samples of which is S squared. That is the best guess at what sigma squared, the population's variance, is going to be. Now, to draw inferences about what's happening with the variance, since it's a squared distribution, we can't just simply sit back and use Z and T. We're going to use something called the chi-square, and the chi-square is nothing more than an additive run of a bunch of z's that are squared. So imagine z squared sub 1 plus z squared sub 2, and on and on and on. That collection of z squared makes up the chi distribution. And it's a really simple distribution when you think about what it is. It's a ratio of what we have from sample variance to population variance times the degrees of freedom. And that thing we call chi-square, and you'll see it here in notation, chi-square degrees of freedom, is important. We'll use the chi-square quite a bit. It's one of the most widely used distributions, but for us, chi-square will represent what we do when we look at a particular variance. And the chi-square, as we see it here as a statistic, is nothing more than I said, the variance of the sample, variance of the population, and the degrees of freedom. If you don't recall degrees of freedom, you should have had this a while ago, but degrees of freedom tells us how many of the observations that we're looking at here are free to vary, given that you have to hold out at least one to balance. So if you have n observations, you have to hold out at least one of them to make sure it always balances. So in this case, n minus 1 is degrees of freedom. When you have multiple samples, as we saw in Chapter 10, sometimes you got to hold out 2 based on the number of samples you have. So this is more of a statistic for us to look at that helps us look at critical values, which can be converted into probabilities for norms in versus norms dist. The chi-square distribution is a very interesting distribution because it's squared. Notice it's only in quadrant 1, so everything is going to be to the right of this up and down line, the y line. It's really almost, in this case, asymptotic on left and right. As we increase the degrees of freedom, you notice as we increase the sample size, it looks more and more normal. That's the point. It really is a normal-ish distribution, and it becomes more and more normal as we increase degrees of freedom. But you'll notice they aren't very symmetric. You have a much steeper, heavier tail on the left than on the right. As we do increase degrees of freedom, it becomes more balanced or more symmetric. We can capture area or probability in this case in the upper tail, what goes past where our threshold is at an upper tail. And you can use a table if you want. That's kind of old school. What we do, if we know that we have a sample size of say 11, so we have 10 degrees of freedom, 11 minus 1 is 10. We want to know of an alpha of 0.05. We want to have at least 5% in the upper tail. We can figure out where the threshold would be. In this case, what is the actual chi-square value here, knowing that it's 0 here? We can create the value of 18. We also can know at 5%, if we know that 18 is our 18.307, this is our place, kind of our placeholder, our line in the sand. 18.03 is here. How much probability is to the right of it? So it's taking consideration everything you have, how far out onto the tail is left beyond you. You can just reverse that. So we use the equals chi-square dot inv. Remember, inverse gives us value, and then we're looking into the right tail. Left tail would just, as you'll see, we manipulate with 1 minus. We'll see that here in a bit. And if we want to find the p-value, we use the dist with the chi-square and the right tail, and that's how we get the 5%. Happens time and time again. Left tail is pretty easy. You just take what you did in the right tail, and if you recall in these distributions, let me go back here. Normally, in our normal z and t tables, if you ran probability from left to right, you'd start at 0 and go to 100% under the curve. However, with chi-square and then with f, it actually goes from 0 on the right to 100 on the left. So this is your actual lower 5%, and this is your upper 5%. I know it's a little convoluted, but squaring it just flips it over. So if we're saying to the right is 5%, then to the left, it will be 95%. So if it's 5% on this side, then the upper 5% means that we up to the 95% threshold right here. That's why we would put in, if we're doing an inverse function, 0.95 versus 0.05, left, right, okay? You can see that here. You can use the inverse function here as well. So it's quite interesting to see how this whole thing plays out for us. Now, we can create confidence intervals for this as well. Notice we take the degrees of freedom times s squared. This should look a lot like the chi-square, except that in the denominator, normally we have sigma squared here and here. Now we're trying to find out what is the confidence interval for sigma squared using chi. So the sigma squared is not there because we're trying to capture it in here. So we need to know the sample size to get the degrees of freedom. We need the s squared. There's two things we need to know. Then we need to create these chi-square values. Notice one is alpha over 2 degrees of freedom. One is 1 minus alpha over 2. So if this was, we wanted a 95% confidence interval, we'd have the 2.5% off to the, the 2.5% off to the right, 2.5% off to the left. Notice they're kind of reversing what you did before. And so, really, and to be perfectly honest, you can create these statistics, 19023 and 2.7, using this, even if you don't know which one goes where. You know the numerators have to be exactly the same. When you divide them, even if you accidentally had 4595 on the left and 652 on the right, I'm hoping you've got this down so smoothly that you could flip them around quite easily and know that it goes from 652 to 4595. Now, this isn't like the others where you're trying to capture 0. It's darn hard to capture 0 in here because it would have to be 0 on the left to capture 0. We're trying to figure out where the variance is. And if I took the square root of this side and this side, boom, boom, you can get a confidence interval for the standard deviation. Just take the square root of the left, SQRT of this equals SQRT of this, and you can generate it. You can do hypothesis tests as well. Same as always. If you can do I swear, if you can do one hypothesis test, you can do them all. This is a two-tailed. This is an upper tail. This is a lower tail. Notice where the beak is pointing. And notice again, all the equalities are in the null. The one thing is our test statistic is exactly what we saw before. It is our chi-square statistic. If you can calculate the chi-square statistic and you know alpha, you get your p-value. So with this, we can run hypothesis test. Say I want to know, is the variance for the returns of something a metals fund, we saw that before in another example in Chapter 10, is it greater than 625? Well, this is an upper tail test. Notice the equalities here in the null. We have a sample of size 10, so we have 9 degrees of freedom. That's where the 9 goes. We know that the sample standard deviation here is 3713. Let's square it. And we're going to divide by 625. So we know that with 9 degrees of freedom, the chi-squared statistic is 1985. Now the question is, what is the chance that I could go out, draw a sample of size 10, think about this, draw a sample of size 10, get this as my standard deviation, get that as my standard deviation, and still not pass this threshold? Well, I want to know what's the chance I could actually see what I just saw. So I just saw this. This is what I expected to see. So what's the chance of seeing what I just saw? If that number is really, really small, say 0.0001, if there's a 0.0001 chance of seeing what I just saw, but I just saw it. It's pretty significant. That's kind of like saying what's the chance that an alien's going to land in my backyard tonight? Well, there's like no chance of it until it happens, and then when it happens, you say, well, I truly believe it. So in this case, if we can prove that, so what we do is we can take this 1985, and we could take that, put it into a chi-square dot dist value dot right tail, put this in with the degrees of freedom, and we can get a value. Now, you can do it with a t statistic. I'm sorry, with the critical value test, and you can get a value and say that heck, what I just found was greater than that, or you could plunk it in into Excel. And here's another example of how to do it. Here's one where we want to know if it's, and in this case, I'm sorry, in this case we do find it's pretty darn far out there. We would reject the null, and you would find that if I were to convert this to a probability, it is a much smaller value than 5%. But to do it, let's get another example. Here, sample is size 10. We have a variance of a sample of 11.07, and we're trying to see if we can find that the variance differs from 72.25. I plunk that in there, and I get a chi-square with 9 degrees of freedom. Sample size 10 minus 1 is 9, 1527. Here's what I was saying. Chi-square dot dist dot right tail. Put your chi-square in, put your degrees of freedom in, and you get the one tail. If you want a two-tail, just multiply it by 2. And you find out in this case a two-tail p-value is 16.76, which is pretty darn big. So you probably won't reject the null, knowing that most often alpha is 0.05. Won't reject the null, and you'll find that these things are not significantly different. So in this case, you can't reject the null, and you find out the variance is not statistically significantly different than 72.25. That's what we're saying here. The last thing is how we look at the ratio of two variances, so we can look at comparison of variances. This is using the F distribution. Z, T, chi-square, now F. There's not too many more left that we'll conquer, but there are many more in your statistical career that you'll conquer. F is very important because it ratios the two by looking at two separate samples of variance, and we use their degrees of freedom, both 1 and 2, in the calculation of the statistic. Now, each has its own, and no, they don't have to be of the same size. It's often asked. In academics, they tend to be. So, reality is you're going to probably see them here, but they don't have to be. So, just like we saw with the chi-square, 0 to 100% versus Z and T, which starts here, goes 0 to 100. And I'm going to use it, and you can use tables if you'd like, but now we have this wonderful thing called Excel that allows us to do the same kinds of things using the inverse value function right tail. And just like before, we want the left tail. If we're looking in the right tail outermost 5%, if we want to look in the left tail, we could continue with the right tail, but put 0.95 in here for the 2. So we have degrees of freedom 6 and 8 in the upper right tail 0.05. If we put 95 in here, the right tail actually turns into the left tail, and you'd find you could get a critical value there as well. There's some convoluted pieces here. I'll leave this up for a second or two. You can see that we can start off by looking at how do I find the lower or left tail by reversing the degrees of freedom and taking the inverse function and all this kind of stuff. Or, more easily done, it's hanging up on me here. Back up one. You can just flip out from the 0.05 to 0.95 for the inverse. Just to be clear, you can also use the f.dist.right tail to calculate your p-values, and you can flip-flop there just the same. So, I'm a fan of Excel. I've got lots of examples out there. It's easy to follow those along. You can calculate confidence intervals for the ratio. This is a rarely asked event, but it's here, so we might as well take advantage of it. The ratio of the two variances, so there nothing changes there. You take 1 over f, where you look at alpha of the 1, 2, versus non-ratio 1 to f. We have alpha over 2, but we have the 2 reversed. Now, again, we just saw that we can do that using the f dot in dot right tail and flip-flop alpha versus 1 minus alpha in that spot. So if you wanted to do that, you could. Here's how we could do this and create. So we can create a 95% confidence interval for the variance. Again, not something that gets asked all that often. Notice 0. You're not going to capture 0 in here. Nearly impossible. It's just to give you a sense of where that variance range would be. The thing you will do is see whether or not two variances are equal to something on the ratio, greater than or less than something. Now 1 is here, but that doesn't always hold. It could be 0, it could be anything. But what we're going to do is simply take the ratio of the two variances to get us the F statistic. So if I want to get what is F, well, the test statistic is nothing more than the variance of 1 and the variance of 2, their ratio. And so what I'll do is take those ratios, and let's just say I want to determine whether or not section 1 and section 2, whether or not the variances differ. So can I look at ratio 1 and 2? And so in this case, we want to look at magnitude. I want to know, can I ratio them out and get 1? Or is it something other than 1? Is it more or is it less? I don't care. I'm just trying to see it. Well, we just did the test and we here before with the confidence interval and saw that. In terms of the hypothesis test, let's see what we can do. Well, since 1 is in this ratio right here, we cannot reject the null, and we have to say, hey, 1's in there, so therefore, the ratio of 1. Can't say that it statistically significantly varies between the two of them. One-tailed F-test, easily done, right tail, and again reverse for the other. Here's an upper tail test. We can look at ratio greater than, there's the upper, notice the equal sign here in the null, and there's all kinds of tests and things that can be done moving forward. Just a couple of things here to plunk in. This is using critical value testing. But more importantly, the one I want to point out is when you have data available, and there will always be data available, believe it or not, there is a function in Excel called the F-test. So if you did equals f.test, you can actually calculate p-values directly from your data, and it will do all these calculations for you. That's it. Just want to give you some intro to chapter 11. Just put some stuff out for 12 and 13 soon, and we'll go from there.